Hello, welcome back. Happy Wednesday. It's another episode of Stats with Mats. This one is dedicated to understanding and interpreting multivariate regression. The logic here is identical to bivariate regression, except we are going to introduce a concept called partial correlation because that's what the equation is doing. Instead of establishing one piece of correlation between an independent variable and a dependent variable, what a multivariate regression equation will do is divide correlation to multiple x's. And that's a pretty cool thing. So without further ado, let's get into it. Last time, we went over the regression equation again and learned how to do it by hand and practiced the interpretation of it. So regression, we are estimating what is the effect or the change in y, which is your dependent variable, if you assume a 1 unit increase in x, which is your independent variable. So it's the magnitude of change in the variable that you care about predicting, independent of any other factors, okay? And we express it in the units of the dependent variable, which is one of the coolest things about regression, is you can price out exactly how much in known units y, or the dependent variable, will change. Now, as I've said, this simple equation of y equals bx plus a plus e, that can handle a multivariate nature as well, okay? So what we're going to be doing here is something known as partitioning variance. If I take the previous example of x and y, it's a little bit hard to theorize about multiple x's because I did not assign units to that. But if you remember my example of the police cars, right? I had squad cars on I-94 and I had average speed, right? So we can say that, yeah, the number of police on the road probably is meaningful here, but there might be some other variables that matter. For example, what about time of day? What about how fast these cars are capable of going? That probably plays into the calculation of the independent variable, of the dependent variable, pardon me, as well. So a multivariate equation or multivariate regression, it uses the same type of OLS solution, but it's going to partition the variance, right? What I thought of as partial correlation of the variance in y to multiple x's. Put another way, multiple independent variables are going to be used to predict the value of the dependent variable, okay? So for example, what if we wanted to understand years of education and its effect on respondents' income? I assume that's important to you guys as you work through education and try to make money throughout a later point in your life. That's classic bivariate regression, but at the same time, we can all theorize about other things that play into this. I think in one of my last videos, I may have said this. I guess I can't quite remember. Nobody would argue, I think, that just years of education is the only thing that affects a respondent's income. So we could also say, all right, well, I would want to also control for what you studied. So not just year of education, but what was your degree path? Not just years of education, but what your sex is, let's say, or race, ethnicity. These are all things that a very cursory glance at the sociological literature will tell you statistically are meaningful predictors of income. So these other factors now need to be put into the equation as well. Does that change the equation? Yes. Does it change it dramatically from what you expect it to look like? No. And I'll show you why in just a second. So the regression equation, it will estimate the effect for each x while holding all other x's at their means. That's the process of partitioning variance. So put another way, let's say I have 3 variables here, the dependent variable of respondents' income and then the 2 independent variables of years of education and sex, right? Just to stick with the example here. The equation then will estimate B For education, B being the regression coefficient or the slope coefficient, for education while assuming that sex is held at its mean. And it will calculate ineffective sex while assuming that education is at its mean. That's the process of partitioning correlation and trying to separate the effect of one variable from the other variable. And looking at it all together, you can get a pretty good sense of the things that affect something that's very important to many of us, like how much money you make. So what does that do to the equation? Nothing that you can't handle. The OLS equation, when you add a second independent variable, we're simply going to be using x1 and x2 to identify which variable responds to what. So when y equals b1, so this would be a multivariate equation with three predictors. Y equals b1 x1 plus b2 x2 plus a plus e. If you estimate the effect of two independent variables, you now have two slope coefficients. You have two b's to interpret. Hence the pairing of b1 x1 and b2 x2. What if you add a third independent variable? Well, by this point, I think you should see where this one's going. Y equals b1 x1 plus b2 x2 plus b3 x3 plus a, always a y-intercept, plus e. So now I have three slope coefficients representing the independent effect of three different independent variables, all estimated while holding the other two x's at their mean. And what this equation does is it finds the smallest squared error across all x's, not just one x at this point, but across all x's. And it partitions the greatest amount of variance that it can across the predictors that you have chosen to include. One way that I like to think of it, here's like kind of a visual that helped me understand regression when I was first being exposed to it. Think about it like a magnet. If I take a magnet and put it next to something like another magnet that is attracted to, then it pulls that other magnet and sticks to it. Think about regression as kind of doing that. You have this scatter plot of all this variation. Inserting an independent variable or an x into the equation acts like a magnet, and it will suck out all the variation that it can reasonably explain. Then you add a second magnet, except this magnet is only attracted to the variation in y that it can explain. You do this over and over again with new magnets sucking out the variation that it is most attracted to. Anything left over is just error term. Does that make sense? I hope so. Okay. So the process here is it's called partial correlation. Partial correlation is, as I have alluded to, the relationship between two variables, x and y, while eliminating the influence of others. When I say eliminate, I do not mean remove it from the equation. I mean, what's the effect of education on income over and above what the effect of sex is? And vice versa. What is the effect of sex on income over and above the influence of years of education? The terminology that I want you to get comfortable using here is net of other effects. When you had a bivariate regression problem, you could explain the slope coefficient using the phrasing of a 1 unit increase in x is associated with a b unit change in y. Now you will have to add net of other effects on the end of that if you have multiple independent variables. So not terribly complicated, but you have to make sure that you identify each slope coefficient as being expressed net of other controls and other factors that you have included within the equation or the model and equation being identical in that case. So today, my goal is to help you understand interpretation of a regression table, because at this point, you are not able to do this by hand anymore. Let me put it this way, because granted, I've clearly been the type of teacher where, like, if I can make you do it by hand, I have done so. But let me put it this way. The final for this class, if we had a normal final, is usually 2 hours and 15 minutes with multiple problems that students are asked to complete. If I asked you to do a multivariate regression problem, that alone would take you over 2 hours and 15 minutes, and there'd be no time for anything else. Hence why we're just going to interpret. And the goal today is to interpret interval level independent variables. Okay? Next week, categorical. We'll look at nominal/ordinal variables next week, using the same logic, though. It just, the interpretation will change depending on what X is. But this is very cool because we can include anything we want as an independent variable here. Anything we want. The only condition here is that your dependent variable must be interval. So let's go back. I teased this last video I created by showing you what a regression output in Stata would look like. This is the same style of hypothesis test, but it's a bivariate regression problem for only for a different variable, and it's bivariate. I should say it's bivariate in that I am predicting number of children. That's the outcome that I care about. That's my dependent variable. And the one factor I'm going to use to try to explain that is years of education. That's my independent variable. So anytime I ask you to interpret regression coefficients from this point on, it will look like this. It will not be a weirdly organized. It will be exact Stata output that you will be getting used to through these lectures. So let's start with the coefficient. We find the coefficient, or what I have been referencing as the B value, under the COEF column. Can you see it? There it is. That value, it is to the right of the name of the variable and in the column marked as coefficient. That's the B value that tells you the effect on Y given that 1 unit increase in X. Now that looks like a pretty small number. Yeah, I understand that. It is a small number, but that's because there's not a lot of variation in number of children. The fact that this is being predicted like you only have 0 to 8 essentially is not a ton of variation. So you would not expect there to be there's not going to be anything that leads people to have an extra 8 children, except fertility drugs, I guess. But we don't have data on who did that in the general social survey. So a 1 unit increase in X is associated with a change in Y. Using that, I'd like you to write down or to say out loud how you would interpret this coefficient for education. Okay, here's how I would interpret this. A 1 unit increase in years of education is associated with a 0.13 unit decrease in number of children. Why did I not say net of other effects after just saying that on a previous slide? Because it's bivariate. On the next slide, or when I add a multivariate nature to this equation, then and only then do I have to say net of other effects. So how do I know it's a decrease in number of children? Look at the sign. Negative 0.13022. If the coefficient there has a negative sign, it's a decrease in the dependent variable. If that value under the coefficient column is positive, so it would lack a negative sign, that means it's an increase in number of children. or the dependent variable, whatever the dependent variable happens to be. All right, there's some other cool stuff here to go through. First, let's think about significance. I let you get off easy last time by saying I'm not going to make you do it by hand. But here, you didn't have to do this by hand. You just had to type, as you can see the command up here, reg child's educ. Okay, so where do we figure out if something is significant? Remember how we always set our alpha level, unless we were specifically told otherwise, at 0.05? We're going to want to find the column with the p-value here. That right there is the number you should be looking at to determine whether or not this is a significant finding, because it might not be. You can regress variables and not find a significant situation, not find a significant relationship. But the value in that column, the p-value, must be less than 0.05. If you see a value there that is greater than 0.05, then there is not a significant relationship between the two variables. But if you see a value less than 0.05, it is significant beyond the 0.01 alpha. Now, what does this 0.000 mean there? That doesn't mean actual absolute zero. What that is referring to is that the true probability level, like the true alpha level beyond which this is significant, is actually less than 0.000, less than 0.001. There is you would reject the null hypothesis in this case with 99.9% confidence. This number, the p-value, is so small here, it's actually less than 0.001. Put more intuitively, there is less than 0.1% chance that you would observe this coefficient, this relationship in the data set, if it was not real, if it was just sampling error, or if it was just random chance. It is very unlikely for you to have found this relationship. Therefore, it is significant. So anytime you see 0.000 in that probability value column, you have a highly significant relationship. But if that value there was 0.532, that means there's over a 50% chance of you just getting this by mistake. So if I saw a p-value that was that high, I would then say there is no significant relationship between these two variables. Okay, so the key thing to understand here, a value of 0.000 does not refer to zero. Really? Yeah, apparently. No, it means that this p-value, this is significant beyond the 0.001 alpha. We would reject the null hypothesis with extraordinarily high confidence. All right. So 99.9% confident we can reject the null hypothesis. One more cool thing to show before we go multivariate. The Y-intercept. I showed you what this looked like on our hypothetical X and Y answer the last time that we met. The constant, find the row that is attached to underscore CONS, which is the constant of the equation. Right there. So the constant there is 3.630329. So let's just round that to 3.63. That is the Y-intercept of your model here. So in this bivariate equation, when years of education is 0, when somebody's when a respondent has 0 years of education, they are predicted to have 3.63 children, which is significantly more than the mean here. And so what that tells you is the fact that that education relationship is negative. That makes sense because the mean person has about 13 years of education in this sample. And the mean person, the mean number of children that people have is I think 1.89 in this data set. So in the absence of any education at all, that number went much higher up from the mean. The baseline here, when education equals 0, Y, or number of children, equals 3.63. So what's my interpretation there? Very simply, I would say when education equals 0, respondents have 3.63 children. Voila. Okay, again, and I think I just lied there. One final thing to show you before we go multivariate, the R squared. Another thing I don't require you to calculate by hand, but the R squared is a measure of how much variation, what is the percentage of variation in the dependent variable that is explained by the independent variable or variables that you have added to your model. And that's right there. So if you're asked to interpret the R squared, here's how I would do that. I see that 0.0621, that should be understood as a percentage. So we move the decimal point twice and it becomes 6.21% of all variation in number of children is explained by level of education. And that's what you're responsible for. Those are the 4 most important things to look at in a regression equation. We want to look at the value of the coefficient. We want to look at the p-value and its significance. We want to look at the baseline Y-intercept, and we want to look at the R squared. R squared is regression's version of ANOVA's eta squared or chi-square's, Kramer's V, where you were able to price out, like to get the percentage that got at the strength of the relationship. So I can look at this and say that, all right, well, this is a significant thing. Education does influence number of children, but 6.2% is, that's kind of small. Like I can probably do better by controlling for other factors. Okay, so I'll repeat this one more time. R squared, it is what is the percentage of overall variation in the dependent variable that is explained by the independent variables in the equation. All right, let's go multivariate. What else did I want to put in? Age at first marriage. I'm hypothesizing that that affects how many children people have. So adding a second independent variable, age at first marriage, take a look at the education coefficient now. Notice how it's a little bit different. What we're doing is something called stepwise regression. You don't need to write that down, but stepwise regression means you insert your independent variables one at a time to see the changes to coefficients as you add them in. So adding that second variable, the education coefficient is now negative 0.114. So it's dropped a little bit, but is it still significant? Yes, it is. So even though the estimate changed a little bit, it's been fairly stable, even with the addition of that extra variable. So what do I want to do here? First, I want to look at my p-value. Is age at first marriage significant? It is. And I know that because this value here is less than 0.001. And what's the value of B? Okay, I'd like you to either say out loud or write down in your notes. What's your interpretation for age at first marriage? For me, looking at that coefficient of negative 0.053, I would say a 1 unit increase in age at first marriage is associated with a negative 0.053 unit decrease in number of children, net of other effects. It's not correct unless you demonstrate that this is net of other effects. Also, look at what happened to my R squared, 0.1036 now. You see where I'm looking at up here, r squared. Now, these two independent variables that I've included, those independent variables together account for 10.36% of all variation in number of children. Not bad, huh? All right, so what did I do there? Well, all I had to do was interpret each coefficient as net of other effects. I had to check their significance, and I interpreted the B coefficient. And notice how, and this is pretty crazy, but notice what happened to my constant. This is an area, there are certain times where the Y-intercept does not make a lot of intuitive sense because it's the value of Y when X's are set to 0. In a multivariate equation, it's when all X's are set to 0. So this would imply, notice that the Y-intercept is now 5.06. That's the number of children you have if you have 0 years of education and got married when you were 0 years old, which is crazy. One of the way... a way that this can be adjusted without going too much into something you're not responsible for, there's a control method. Like if you have a variable where it makes no intuitive sense, like to say you got married at 0 years old, you can set the Y-intercept to reflect a 1 unit, like to reflect what it is when everything together is set at its mean. And that's called group mean centering. It borrows some of the logic of ANOVA, actually. And so what that would do is it would be what's the baseline number of children given an average age at first marriage. So, to do with that knowledge what you will. But when those two vary, when somebody has 5 children when they get married at 0 years old, I'm just going to move on because that's making me uncomfortable. Anyway, third. Let's add a third variable. Nothing more complicated than b1x1 plus b2x2 plus b3x3. So don't jump the gun here. Check that p-value, baby. Hours worked has a p-value of 0.133. So as I have been asking all semester, is 0.133 less than 0.05? It is not. So what's the right interpretation here? Hours worked is not a significant predictor of number of children. You do not need to interpret the B coefficient if the p-value does not register significance. I will repeat that. You do not need to reference the coefficient if the p-value associated with that coefficient is less or is greater than 0.05. You do not need to reference B if the p-value is greater than 0.05. So the correct interpretation, hours worked is not a significant predictor of children. That wasn't too difficult. And if you notice, my r squared barely moved. Putting in hours worked did not improve the amount of variation I explained, really at all. And that's because it's not a significant predictor. It's not attaching itself. Like, remember my analogy of the magnets? It's like putting a magnet in an area with other magnets and nothing happening. So it did not improve the model fit, as one might say. But controlling for hours worked did alter the findings of age at first marriage and education. The coefficients changed slightly, but they never became insignificant and they never switched their sign. They maintain negative relationships with number of children they have. Okay. All right. I want to add in one more predictor here. Age. I want to add in age. Because I hypothesize the older you are, the more chances you've had to have children. And let's say that maybe that's associated. So a 1 unit increase in age, again, looking at the p-value to establish significance and then looking at the B coefficient, a 1 unit increase in age is associated with a 0.032 unit increase in number of children net of other effects. I can't forget that. And notice how I added another 6% to my R squared. Now these four independent variables, account for 16.5% of all variation in Y. Education is still a negative and significant effect. Age at first marriage is still a significant and negative relationship. And hey, look, hours worked turned out to be significant now. So what's going on there? Hours worked, notice how that's a very small effect. And this is something that it may have just now registered significance, which I can tell because 0.018 is less than 0.05. This is one of the things that tends to happen through stepwise regression. What you're doing now, like by adding in a separate piece of information, an additional X, the model gets a better idea of how to partition variance. And so there was likely a whole bunch of like kind of muddled variation that wasn't really being assigned anywhere. And it was making the hours worked relationship variable look insignificant. The more information I add to the model, usually the better of a job it does in estimating all coefficients, because the equation needs to make decisions. How much variation goes to X1, how much to X2, how much to X3? You got to have those additional X's in order for the equation to do a good job of distributing partial correlation. All right, so I realize that that's probably sounds kind of theoretical. It makes regression kind of sound like an art form. In a way it is. But here's the key thing to know. It's almost like you're adding to the sample size, essentially. Each additional variable bestows more information to the equation. And that extra information means the equation gets better at partitioning the variance in Y. Okay? There is a limit here, though, and it's an important limit. The limit is that at a minimum, you want to have at least 10 extra observations, but really somewhere between 25 to 50 is really all I would feel comfortable with. You want to have, for me, I like to have no less than 50 observations per X that I include. So if I have a bivariate regression equation, I want 50. Really, that's what I'm looking for. If I have 2 X's, I want 100. 3, I want 150. 4, I want 200. Sometimes you can get that. And actually, in my case, I can always get that because I just happen to use large cross-national publicly available data sets with 50,000 Europeans in them. But nevertheless, you want minimum 10 and really around 25 extra observations per X. So if you have too many independent variables and you don't have the sample size to support that, the terminology we use for that is called overfitting the model. And in that case, it will mess up the estimation of the coefficients because it doesn't have enough degrees of freedom to appropriately estimate and average out what the effective B really is. Okay. And one of the things I don't think any of you really looked at is in this, if you go back through this video here and you look at the sample size for the very first bivariate model that I fit, I had about 45,000 respondents for 2 variables. But by the time I got to those 4 X's, age at first marriage, education, age and hours worked, I dropped to 702. Where can you see that? Number of observations right here, 702, which is fine for what we're working with here. That is more than enough statistical power. That is plenty of degrees of freedom. But be aware that each time you put a new X into the into the variable or into the model, each time you do that, it will estimate the coefficients for only the variables or for only the cases that have no missing data across all of the variables that you've included. So put another way, if I go back here, These are the 702 people who answered the question for how many children they have, their years of education, their age at first marriage, their number of hours worked in a given week, and what their own age is. It's pretty much just one variable that screwed this up for us. Because you remember, education's got like 17 non-valid cases, age has like 20. The one big one here was we included age at first marriage. Put another way, we are predicting number of children you have for only people who have been married. And that's 702 people in our data set. Keep that in mind. That is that's a condition. So really, when we're interpreting, I'm not going to ask you to do that, but the unsaid assumption here is that our model only predicts number of children for those that have been married. There are other ways and better ways to get at this, but it involves using categorical controls. And that is where we're going with this. I did want you to see just the addition of one variable cut my sample size in like to shreds. All right. But the first thing for Friday, I would like you to do a bivariate regression by hand. So that's the assignment, and that's going to be the next video. We'll be going over that. Don't let this one get away from you. Get your work in, and please, please, please let me know if there are any questions at all. Thank you very much. Take care of yourselves.